All right, so we have these special right triangles. Okay, so a right triangle just means that it has a right angle. Sorry, one second. Sorry, it's not connecting. Hold on. There we go. Okay, so a right triangle has to have a right angle symbolized by the little square, right? That means it's a perfect 90 degrees. Okay, so there's many different right angles, right? Like this, or this would be a right triangle. This could be a right triangle. This could be a right triangle. But there's two special right triangles that have extra properties that we really care about. So the first one is the isosceles right triangle. Okay, so isosceles means two congruent sides. Okay, so you can tell by these little markings that these two sides are the same length. Okay, and this one does not have a little tick mark, so you know it's different than the first two. Okay, so let's just focus on that one right now. Okay, so again, this is an isosceles right triangle. It's isosceles because there's two congruent sides, and it's right because there's a right angle. Okay, so if we look down here, we're going to solve for the missing values if a equals 3. Okay, so I'm just going to redraw it so it's not too crowded. Okay, so we're told a is 3. Okay, so we're just doing what the problem told us to do. Well, through these markings, we know that these two sides are congruent. So if a is 3, then b is also going to be 3. Okay, so now C does not have the marking, so it's not 3 as well. But now that we know two of the sides, we can find the third through the Pythagorean theorem. Right, so we want to recall that for right triangles, not for all triangles, only right triangles, a squared plus b squared equals c squared. And c has to be the hypotenuse. Which is the vocab term for the longest side of a right triangle. Okay, so again, this is known as the Pythagorean theorem. Okay, so we can use this to solve for the missing side of the right triangle over here. Okay, so a is 3, b is also 3, and c is unknown, so we'll leave it as c squared. Okay, 3 squared is 9. This 3 squared is also 9. 9 plus 9 is 18. To get the c by itself, to undo the squared, we would square root both sides. Okay, so let's see if we can simplify the square root of 18. 18 is equal to 2 times 9, which is 3 times 3. So 18 is 2 times 3 squared. Okay, so we can take the 3 out and leave the 2 inside. Right, just to be clear, right? Because it's a square root with an invisible index of 2, you can't take this out because it only has an exponent of 1. But the 3 has the correct exponent, so the 3 gets to move in front. Okay, so we can simplify to 3 radical 2. Okay, so when a is 3, b is also 3, and c is 3 radical 2. Okay, so that's a way of calculating the side lengths for a isosceles right triangle. We also want to learn one other type of special right triangle. Okay, so this is the right triangle created by the altitude of an equilateral triangle. Okay, so there's a lot going on in that description. So first, equilateral, we want to know that that means three sides congruent. Okay, so all three sides are congruent in an equilateral triangle. Next, altitude. What's an altitude? So the original triangle was this whole thing. So an altitude is where you start at one of the corners, the vertices, and you draw a line straight down that hits the other side in a right angle. Okay, so that's what we did here. Again, the original triangle was this. We drew in an altitude, and then we only kept this half. We threw this half away. Okay, so again, this is the special right triangle, just this part, not this part. That part got thrown away. Okay, so let's see if we can find the side lengths of this one also. Okay, so again, I'm going to redraw this off to the side. Okay, so we're told to use A is 3. Okay, so we don't have any congruent markings this time, so we can't just call another side 3 as well. Okay, so we can't do the Pythagorean theorem yet because there's two unknowns, right? You can only solve for one letter at a time. You can't do anything when you have two letters. Okay, so we got to figure out either B or C first before we can apply the Pythagorean theorem. Okay, so maybe thinking back to the original setup, see if you can figure out either B or C. All right. Anyone think they know, Dimitri?
C can be found.
Okay.
Multiplying A 2 times because A is equivalent to 1/2 of C because it's an equilateral triangle.
Okay, good. So Dimitri said that A is half of the full side, basically, right? Because these two pieces are equal. So the original full side is double A. Okay, so if A is 3, C is double that, right? Because you'd have 3 here and another 3 here makes 6 total. And since it's equilateral, if this is 6, this whole side is also 6. Okay, so now that we have 2 of the 3 sides, now we can apply the Pythagorean theorem. But be careful about your order. Remember, C is always the longest side. So we know A. We don't know B, so you keep it as B, but we do know C. Sorry, that should be a equal sign over here. Okay, so 3 squared is 9. Sorry, we know that C is 6. 6 squared is 36. Okay, so this time we can't square root right away because the exponential term is not by itself. We need to get rid of this 9 first. The 9 is getting added, so let's subtract 9 from both sides. And now that the exponential term is by itself, we can go and square root both sides. Okay, so the square root of 27. 27 is equal to 3 cubed. but it might be more useful to call it 3 squared times the leftover 3, right? So that you can take a 3 out front. Okay, so for the half of the equilateral triangle, when A is 3, B is 3 radical 3, and C is 6. Yeah, I'll deliver. Thank you. Okay, so that's the strategy that we can apply. Okay, so for the second question, I want you to forget about the first question when we said A was 3, and I instead want you to calculate it if A were 10 instead. Okay, so again, do it for both triangles. For this triangle, if A is 10, what is B, what is C? And for this triangle, if A is 10, what is B, what is C? Okay, so go ahead and give it a try. If you finish that one, continue on to the next. Okay, so hopefully what you came up with, if A is 10 for the isosceles right triangle, B would also be 10, and then C would be 10 radical 2. For the half of the equilateral triangle, if A is 10, then B would be 10 radical 3, and C would be 20. Okay, so you can keep going, but you can already clearly see a pattern, and you likely have been introduced to these special right triangles before. Right, so we see that for the isosceles right triangle, the two shorter sides are equal, and the longer side, the hypotenuse, is just the shorter side times radical 2, right? 3 times radical 2 equals 3 radical 2. For the half of the equilateral triangle, 3 times radical 3 is 3 radical 3, or 3 times 2 would be 6. Okay, so let's just jump ahead and write our patterns down here. Okay, so for any isosceles right triangle, whatever side length one leg is, the other leg will be the exact same. And the hypotenuse will be that leg times radical 2. Okay, by the way, the angles for this one, the right angle here is 90 degrees, and you know a full triangle is 180. Okay, so 180 minus 90 leaves 90 for these two angles combined. Since it's a isosceles triangle, these two must be equal. So 90 divided by 2 means both of these are 45. Okay, so now over here. So here, we know this is a right angle because that's how it was created, by hitting this at a right angle. And we know that for equilateral triangle, the 3 initial angles are all 60 degrees. So this was 60, this was 60, and this combined was 60. But since we split it in half, half of 60 is how we know that this one's 30. Okay, so this is also called a 30, 60, 90 triangle. Okay, so this bottom side length, if we call that x, we saw that the medium side is x times radical 3, and the hypotenuse opposite the right angle is 2x. Yeah, so sometimes it's hard to tell which side is longer. The longest side is always opposite the right angle. Okay, so knowing these side length relationships will allow us to easily find the missing side lengths of any special right triangle. Okay, so let me show you how we can apply this on the back. Okay, so let me jump all the way to problem 12. Okay, so you're told that this is an equilateral triangle and we're splitting it in half. So this is going to form a 30, 60, 90. Okay, so what I would do is I would label the three sides with the same names we gave them on the front page. Okay, so the shortest side opposite the 30 degrees, I'm going to call that X. Okay, so opposite the 30 degrees is X. The in-between side, opposite the 60 degrees, I'm going to call that X radical 3. And the hypotenuse, opposite the right angle, I'm going to label that as 2X. Okay, so the reason we do that is now we can say, okay, well, the side that I labeled 2X is told to us as exactly 16. So 2X must turn into 16. So for this problem then, X would be 8. Okay, so this side that's labeled X is simply 8. And this side over here, X radical 3, now that we know that X is 8, X radical 3 becomes 8 radical 3. Okay, and then I'll do a 45, 45, 90 also. So I'll just do question 1. Okay, so the two shorter sides are both X. The hypotenuse is X radical 2. So this time we're told that X is equal to 8. Right, the X is already by itself, so you don't need to divide. It's just X equals 8. So this side labeled X is also 8. And X radical 2 becomes 8 radical 2. Okay, so one quick note, your answer should be in simplest radical form. So just like before, that means that if you can take anything out of the inside of the radical, you should. It also means no radicals in the denominator. Okay, so go ahead and try finding the missing side lengths for the rest of these. Okay, and again, all of these should be doable without the use of a calculator. Okay, so the implications of this, what we can take away from this. Remember, the whole point of like similar triangles is that the ratios, the side length relationships stay the same. Even if the actual triangles are bigger or smaller, the ratio is the same, right? So like for the 30, 60, 90, the longest side is always double the shortest side, right? No matter how long or short the initial sides are, the hypotenuse is always double it. Okay, so with that in mind, we are able to solve for exact values when these special angles are in a right triangle. Okay, we don't need to approximate, we don't need to round or estimate. We can always find the exact values. Okay, so if you can exactly get all of the side lengths, you can also exactly get all of the trigonometric ratios. Okay, so trigonometric ratios were a big topic in Math 2. So these are things like sine, cosine, and tangent. They represent ratios. They're the comparisons of side lengths. Okay, so that means that for these key angles, we can know sine, cosine, and tangent without a calculator and without having to actually see a triangle because we already know the relationships. Okay, so how do we do that? Well, let's start with the 45 degrees. Okay, so first, let's just convert this back to radians. Again, the one thing I encourage you to memorize is that a full circle is either 360 degrees or 2 pi radians. If you just remember that, you can figure out all the other stuff. Okay, so how do we get from here to 45? Maybe you want to start by dividing by 4. Right, so this divided by 4 becomes 90. 2 pi divided by 4 reduces to pi over 2. Okay, so 90 is double 45, so let's divide by 2 again. Pi over 2 divided by 2, which is the same as pi over 2 times 1/2. 45 degrees is equal to pi over 4 radians. Okay, so now what about the 3 trig ratios? Okay, so we need to remember what each of sine, cosine, and tangent represent. So there's many memory tricks out there. One of them is SOHCAHTOA. Right, so what this means is that SO is representing sine is opposite over hypotenuse. Right, SOH, sine is opposite over hypotenuse. Cosine, CAH, cosine is adjacent over hypotenuse. And TOA, TOA means tangent is opposite over adjacent. Okay, so what this table means is in this box, I want you to tell me what is the sine of 45 degrees. Okay, so again, no calculator. We can figure this out using our knowledge of the side length ratios. So we can do this with any of the triangles. That's the whole point. It works for any size triangle as long as it has those angles. Okay, so the very first one, right? We see this one has a 45-degree angle. Okay, so let's use that one. So sine is going to be opposite over hypotenuse. Okay, so from that 45-degree reference angle, the opposite side is 8. And the hypotenuse, the longest side, is 8 radical 2. Okay, so sine will be opposite over hypotenuse, or 8 over 8 radical 2. Okay, however, this one is not simplified yet. We can actually do a couple of things. So first, we can reduce by 8. Both numerator and denominator can be divided by 8. Okay, so remember, when the numerator is a 1, you have to keep the 1. You can't just get rid of it. Okay, and then from here, we can rationalize this denominator. To get rid of the radical 2, we can multiply by radical 2 over radical 2. And radical 2 times radical 2 is regular 2. Okay, so we figured out that the sine of 45 degrees is equal to radical 2 over 2. And again, this will be true for any triangle, any size. As long as it is a 45-degree angle, its sine ratio will always be radical 2 over 2. Okay, and so let me do one more. Let's jump to, say, the tangent of 30 degrees. Okay, so here I'm going to try to find a 30-degree angle. Okay, so right here. Okay, so for tangent, I want the TOA, TOA, so I want the opposite and the adjacent sides. The opposite side is the only one it doesn't touch. So the only side that doesn't touch the 30 degrees is the 7. Okay, now adjacent's a little trickier, right? Because adjacent means like touching. Well, the angle touches two sides, right? So which one? It's the one that's not the hypotenuse. Okay, so the hypotenuse across from the right angle is the 14. So this is not the adjacent side. This is the hypotenuse. So the adjacent side is this one. Okay, so tangent of 30 degrees will be opposite over adjacent, meaning 7 over 7 radical 3. Okay, and again, let's try to reduce this. We can divide both numerator and denominator by 7 to start. Again, you have to keep the 1 because it's in the numerator. And then the rationalization happens when you do times radical 3 over radical 3. Okay, so this simplifies to radical 3 over regular 3. Okay, so the tangent of any 30-degree angle, no matter what size triangle it's in, the tangent ratio will always be radical 3 over regular 3. Okay, so questions about that? All right, so why don't you see if you can fill in the rest of the table? And again, for practice, let's do this without a calculator. Okay, so some of you may be familiar with this from a previous class. Some of you might be your first time. Either way, again, that's okay. Let's define some vocabulary. So what you see pictured up here is called a unit circle. So this is the circle of radius 1. Centered at the origin. Okay, so there's only one unit circle. There's only one possible circle that fits this description. Okay, so it has radius of 1 unit, and the center of the circle is the origin, the point 0, 0. Okay, and then talking about angles, right? We know angles have two sides, right? So one side will be the initial side. So we'll describe this as the side of the angle which lies on the positive x-axis. Okay, so for standard position, which we mentioned last class, every single angle has its initial side on the positive x-axis. Okay, so every single angle will start right here. Okay, so then what makes them different is their terminal side. Okay, so we'll describe this as the side of the angle which defines the angle. Okay, because again, if all the terminal sides are the same, the only thing that makes two angles different would be their, I think I may have said that backwards. If all the initial sides are the same, the only thing that makes them different is their terminal side. Okay, so the terminal side is what makes, for example, a 30-degree angle a 30-degree angle and not a 60-degree angle. Okay. So we'll define the other two parts later. Okay, but what we're gonna now do with this unit circle is we're gonna, we sort of did this a little bit last class, but we're gonna start by placing a few select angles around the circumference, basically. Okay, so remember, all angles will start on the positive x-axis, but then from there, they'll rotate a certain amount, and the terminal side will form an angle. Okay, so why don't we start by just marking 0 degrees right here. Okay, so since we're starting on the positive x-axis, directly to the right will be 0 degrees. Okay, if you go all the way around, we know that a full circle is worth 360 degrees. So if you go all the way around and end up back where you started, this point is also 360 degrees. Okay, if a full circle is 360 degrees, then half a circle, half of 360 is 180 degrees. Okay, if half a circle is 180 degrees, half of that, half of half is 90 degrees. Okay, and then halfway between 180 degrees and 360 degrees would be 270 degrees. Okay, so that's our start. What we're going to do from there. Okay, so again, all angles are starting on the positive x-axis. So the first key angle we, or not necessarily first, but one of the key angles we talked about in the special right triangles was 30 degrees. Okay, so we're going to want to form a 30-degree angle with at the origin. Okay, so, it's not going to be perfect, but, this maybe, yeah, probably there is about 30 degrees. Okay, so, right, this angle in here, this is 30 degrees. Okay, and then wherever that side, so this is the terminal side. Wherever the terminal side hits the unit circle, let's also mark that point as 30 degrees, just to make it easier to see. Okay, so we just spent a lot of time learning about the properties of right triangles, but this is not a triangle, right? There's some lines, but there's no right triangles. So we're going to create a right triangle. Okay, so from that point on the edge of the circle, you're going to draw a line straight down that hits the positive x-axis in a right angle. Okay, so hopefully you see the right triangle that we formed. Again, it's a little tricky. Remember, this angle is not 30 degrees. The 30 degrees represents this angle, not here. Okay, so now we formed a right triangle. So now we want to figure out the side lengths of this right triangle. Okay, so we learned how to do that when you're given one of the three sides, right? You use the pattern x, x radical 3, 2x. But right now, none of the three sides are given to us, right? We need to know one of the sides. Okay, so by definition, we actually do know one of these side lengths. Does anyone think they know what I mean? Yes, Abe?
Is the hypotenuse the same as the radius?
Yeah, exactly. So Aiden said the hypotenuse of the triangle is also a radius of the whole circle. Okay, and the definition of a unit circle is the radius is 1. Okay, so this hypotenuse is 1 unit long. Okay, so with that information, we can go ahead and figure out the other two sides. Okay, so again, if it helps, you can maybe redraw it off to the side so it doesn't get too crowded. Okay, so in here, we've got a 30-degree angle. This is a right angle. And the hypotenuse is 1. Okay, so using what we just learned on the other worksheet, the 30, 60, 90, the shortest side is opposite the 30 degrees. We call that x. The hypotenuse opposite the right angle is 2x. And the other one is x radical 3. Okay, so for this particular problem, we see that 2x is equal to 1. So we want x, not 2x. Let's divide by 2. Okay, so for this problem, x is 1/2. Okay, so over here, again, x is 1/2. And x radical 3 becomes 1/2 times radical 3, or radical 3 over 2. Okay, so let's go ahead and label those sides back on the unit circle. Okay, so we figured out that this sort of height is 1/2 a unit tall. And down here, it's going to be a little confusing. Notice the triangle doesn't go all the way to here, right? The triangle only goes to here. Okay, so I'll draw a little sort of bracket marking, right? This side length is radical 3 over 2. Okay, so before I continue, are there any questions about what I've labeled so far? Okay, so now if you look at the other handout, the one with like the chart. Okay, so we're basically going to do the same thing I had you do on the previous worksheet. So we'll skip the 0 degrees for now and we'll go to the 30 degrees. Okay, so let's figure out the sine, cosine, and tangent of 30 degrees. Okay, so sine of 30 degrees. Sine is opposite over hypotenuse. So opposite is 1/2, hypotenuse is 1. Okay, well, dividing by 1 is easy, right? So 1/2 divided by 1, anything divided by 1 stays the same. Okay, so this calculation was a lot easier than the other one, right? When we were doing like 8 divided by 8 radical 2 or whatever, that took a lot of simplifying. Here, the denominator of 1 makes the math really simple. Okay, let's continue. Cosine is adjacent over hypotenuse. Okay, so adjacent over hypotenuse, radical 3 over 2, all over 1. Okay, and then again, dividing by 1 makes the math really easy. Lastly, tangent. Tangent is opposite over adjacent. So opposite over adjacent. Okay, so this time, unfortunately, we don't get to divide by 1. This time the calculation is more complicated. Okay, so going sideways, you have 1/2 divided by radical 3/2. Instead of dividing, you can multiply by the reciprocal. The 2's can reduce, but 1 over radical 3, you can now rationalize. Okay, and so again, if you compare this to the other worksheet, you should see it's the same values, even though we're using a different triangle. And again, that's the whole point, that no matter what triangle you use, as long as it's a 30-degree angle, sine, cosine, and tangent will be the same. Okay, so one last thing that we'll do here. If we imagine this as a coordinate plane, we'd also like to know the coordinates of this point where our side hit the unit circle. Okay, so what are the coordinates here? So it's x comma y, right? So from the origin, the x movement was radical 3/2. And the y, you went up 1/2 a unit. Okay, so we're done with that one for now. Okay, so this next one is going to overlap a little bit. So if you have like a different color pencil, you might want to use it. If not, it's not a big deal. Okay, but the next key angle that we'll do is 45 degrees. Okay, so 45 degrees is obviously more than 30 degrees, so it's a little bit past the 30 degrees. Okay, so the 45 degrees should be halfway between 0 and 90. Okay, so I would say about here. Okay, and again, the reason that this line represents 45 degrees is we're actually considering this angle, including the positive x-axis. So we're really saying that this angle that I'm doing the double arcs is 45 degrees. Okay, so again, we want to work with right triangles. So we got to create a right triangle. So from that point where your 45-degree terminal side hit the unit circle, draw the, again, what's called the altitude, the line straight down that hits at a right angle. Okay, so again, right now we're working with this triangle. Okay, so you got to kind of ignore all the numbers from the first triangle. Okay, so for this triangle, the hypotenuse is again a radius of the circle, right? It goes from the center of the circle all the way to the edge. So the hypotenuse is equal to the radius, which is defined as 1. Okay. Okay, so again, I'm just going to redraw this off to the side so it's not as crowded. All right, so this is what we have so far. Okay, well, let's again use the side length ratios we learned for a 45, 45, 90 triangle. The two shorter sides are both x. The hypotenuse is x radical 2. So the side that's labeled 1 is worth x radical 2. So x radical 2 must turn into 1. Get the x by itself. And make sure you rationalize. Okay, so x simplifies to radical 2 over 2. And both shorter sides are equal, so they're both radical 2 over 2. Okay, so this side is radical 2 over 2. And the bottom side, which again is a little confusing, so I'll draw the brackets. Okay, so focusing on that newly created 45, 45, 90 triangle, we can go ahead and again do sine, cosine, tangent on the table worksheet. Sine opposite over hypotenuse, that'd be radical 2 over 2 over 1. And anything divided by 1 stays the same. Cosine adjacent over hypotenuse, that would be radical 2 over 2 over 1. And tangent, opposite over adjacent, opposite over adjacent. So radical 2 over 2 divided by another radical 2 over 2. Okay, so when you divide any number by itself, it equals 1 whole. Okay. And just as we did before, let's go ahead and figure out the coordinates of this point. So the x coordinate, you go radical 2 over 2 to the right, and the y coordinate, you go radical 2 over 2 up. Okay, so 2 key angles done, 1 to go. So again, if you have a third color, you might want to switch. Again, if not, it's fine. Okay, so the last key angle is 60 degrees, which again is double 30. And I'll estimate it to be about right here. And again, the reason that this is 60 degrees is the angle formed with the positive x-axis. We're saying that this angle is 60 degrees. Okay, so like before, we need to form a right triangle. So draw the altitude straight down. Okay, so now we're working with this triangle. Okay, so just like the first two, the hypotenuse is also a radius. So the hypotenuse is 1 unit long. Again, let me just redraw it so it's not too crowded. Okay, so we know that for a 30, 60, 90 triangle, opposite the 90 degrees is 2x. Opposite the 60 degrees is x radical 3. opposite the 30 degrees is just x. Okay, so we've got 2x equals 1. So x will be a half. And then x radical 3 becomes 1/2 times radical 3, which becomes radical 3 over 2. Okay, so let me label those. The bottom side of this was 1/2. And the other side was radical 3 over 2. Okay, one more time. Let's calculate sine, cosine, and tangent. Opposite the 60 degrees is radical 3 over 2. Opposite the hypotenuse is 1. Cosine adjacent over hypotenuse will be 1/2 over 1. And tangent will be opposite over adjacent. So radical 3 over 2 divided by 1/2. That one we probably need to do off to the side. To divide by 1/2, we can instead multiply by 2 over 1. The 2's reduce, and you just get radical 3. Okay, and then let's go and do the coordinates again. So this point it's x coordinate, the horizontal distance from the origin, you went 1/2 a unit right. And then you go radical 3 over 2 units up. Okay, so that's all done. Okay, so next up would be 90 degrees, right? So don't draw this. So 90 degrees is obviously up here. So you would want to form a triangle, right? But we always form the triangle by going straight down. If you go straight down, you don't form a triangle, right? It just overlaps this line. So it doesn't really work. We're going to have to figure out a way to handle this situation, right? All of this was fine, but going straight down means that no triangle is formed. Okay, so that's what we'll try to figure out. Okay, so what I'd like you to do for the rest of the period is get a start on the exit ticket that's posted on Canvas. We'll be continuing this handout next class, so please make sure you don't lose it.